Hi guys, in the last lecture we studied about the performance indices of a transformer. So performance indices were the parameters that we study to judge the performance of a transformer. We saw the first performance indice was the efficiency. We determined efficiency as X into kVA cos phi divided by X into kVA cos phi plus iron loss plus copper loss, which was equal to X square into copper loss at full load. X was the loading of the transformer. And the second performance indice was the voltage regulation, which was I2 into R02 cos phi plus X02 sin phi divided by V1 dash. And for leading loads, we change the plus sign to the minus sign. It can also be written as epsilon r cos phi plus epsilon x sin phi, where epsilon r and epsilon x are the per unit voltage drop across the resistance and per unit voltage drop across the reactance. So these are the two performance indices in case of transformer. Based on that, we judge the performance of transformer, which is performing well and which is not. In this lecture, we will be studying about different ratings that are associated with a transformer and how do these ratings vary with the dimensions of a transformer. So ratings of any machine, there are three types of ratings. First is kVA rating. As I told you, kVA rating is related to temperature rise in a machine. Okay. The better the cooling system of a machine, the more kVA it can handle. Okay. Because the more the power it delivers or dissipates, the more will be the heating in the machine. So you have to apply a better cooling system to keep the temperature down. Otherwise, the machine may burn out. That is why the kVA rating is related to temperature rise in case of machine. Next rating is voltage rating. The voltage rating is related to insulation in a machine. Higher the voltage rating, more is the insulation required in a machine. Otherwise, what will happen? If you use less insulation, then dielectric breakdown may occur and the insulator may start conducting and it will short circuit the winding. That is why insulation is required more for higher voltage rating. Again, I am repeating, at higher voltages, dielectric breakdown may occur, due to which insulator may start conducting. And last, current rating. It depends on cross section area of conductor. Okay. Higher the current, more the cross section area of the conductor is required so that it can handle that much amount of current. If the cross sectional area is less, then the conductor may get burned out. Okay. If you reduce the area, then resistance of the conductor increases. Then I square R losses will also increase, due to which temperature will also increase and conductor may melt. That is why for higher currents we use thicker conductors and for lesser current we use thinner conductors. Like in your laboratories, you use very thin wires because they handle only a current of 5 to 10 amperes, not more than that. But if you see the transmission lines that we use to supply the current, those are very thick as compared to those conductors because they are carrying high currents. Now let us see how do these ratings vary with the dimensions of transformer. First is my voltage rating. When we derived EMF equation, we derived V is equal to 4.44 Fn Bm into An. Remember, whenever we scale the transformer or whenever we change the dimension, we make sure that Bm is constant. Why do we make sure Bm is constant? Because if Bm is increased somehow, then the transformer may enter saturation. So this can lead to saturation. So it is pretty necessary that you keep Bm as constant. That means the voltage is proportional to area. Now suppose I say that all dimensions of the transformer are made root 2 times. All dimensions are made root 2 into original dimension. Then area is equal to 2 times initial area. So voltage will also become 2 times initial voltage. That is how voltage rating varies with the dimension of a transformer. It varies as the dimension square, or it varies directly proportional to the area. Is it fine? We can call it as dimension square. Next is my current rating. Actually, when we are talking about transformer, suppose I am considering core type transformer, this region, this is called as window. So we define a window factor, which is actual cross section area of winding divided by window area. This is called as window factor. Now, if suppose there are n turns like this, and I know cross section area of conductor is A1 on the primary and A2 on the secondary. N1 turns here, N2 turns here. So total cross section area on the primary will be N1 into A1, because area of cross section of each turn is A1. So area occupied by N1 turns would be A1 into N1. Similarly, area occupied by N2 turns here would be N2 into A2 divided by window area. Now, as I told you, area of cross section is proportional to the current rating. So let me call as I1 is equal to A1 into delta, I2 is equal to A2 into delta. So I can replace A1 by delta N2 I2 by delta divided by window area. Now I know, since primary and secondary MMF must be equal, as I told you according to Lenz's law, primary and secondary MMF oppose each other and they cancel out each other. So here I am neglecting the no load current, I am only considering the load component of current. So N1 I1 must be equal to N2 I2. So this kW would be 2N1 I1 by delta divided by AW. So I1 would be AW KW delta by 2N1. Okay. So what I can see here, that the current rating I1 is proportional to window area. Okay. If it is proportional to window area, that means if I scale the transformer, it is also proportional to dimension square. If all the dimensions of the transformer are made twice the original value, the current rating will go up by 4 times. Okay. That is the concept, that current rating is also proportional to area, but it is not proportional to area of core, rather area of the window. But when we are scaling the transformer, area of window and area of core are scaled by the same factor. Okay. Next comes my kVA rating. Now kVA rating can be written as voltage rating into current rating. Okay. Now voltage rating would be 4.44 Fn Bm into An. Current rating was delta AW KW by 2N. So this will get cancelled out. So it will be 2.22 FBM delta KW AN into AW. So KVA rating is proportional to area square, or we can say dimension raised to the power 4. So if we make all the dimensions of the transformer twice the original value, then KVA rating goes up by 16 times. Okay, that is how KVA rating depends on the dimension of the transformer. Next, let us consider core loss. When we wrote the core loss expression, I wrote it something like this. Hysteresis loss eta Bm raised to the power x F into V. So hysteresis loss was proportional to the volume of core. Okay, and mainly in core losses, hysteresis loss dominates over eddy current loss. So what I can say is core loss is proportional to core volume, or we can say dimension cube. Okay, core loss is proportional to the dimension cube. Now, if we see the core loss component of current, it will be PC by voltage, which is proportional to volume by area, because core loss is proportional to core volume and voltage rating is proportional to area. So it is directly proportional to dimension. Okay, that means if dimensions are made twice the original value, the core loss component of the current also doubles. Now, if we talk about inductance, inductance is nothing but mu naught N square A by L. So it is proportional to area by length. So it is proportional to dimension. That means the reactance that we consider Xm is also proportional to dimension. Then if we talk about I mu, V by Xm proportional to area by dimension. So it is proportional to dimension. That is, if dimensions are made doubled, then magnetizing current also doubles itself. Then if we talk about no load current, no load current is under root I mu square plus IW square. It is also proportional to dimension. So as you scale the dimension by 2 times or 3 times, the no load current is also scaled by the same factor. So this is how different quantities in a transformer are related to the dimensions of a transformer. Voltage rating varies directly proportional with the area. Current rating also varies directly proportional with the area. KVA rating varies with area square, and then core losses vary with core volume or dimension cube, and then no load current varies with dimension directly. Okay, so this is how the various ratings in a transformer are defined. Next, let us consider the inductances of a transformer. Now transformer has, if we talk about, transformer has 3 type of inductances. First will be given as mutual inductance, which is M. Self inductance primary will be given as, let us say, LSP. Self inductance secondary will be given as LSS. Now, but when we construct the transformer model, we use leakage reactances and magnetizing reactance. So, reactance is nothing but omega L. So, if we talk about leakage inductance, in case of primary it is LSP minus M. In case of secondary it is LSS minus M, and for magnetizing inductance it is 2M. Now you can create the reactance as omega into LSP minus M, omega into LSS minus M, and omega into 2M. So this is how we can create the transformer model by converting the self and the mutual inductances into leakage and the magnetizing inductance of the transformer. Okay. So that is how these inductances are related to the transformer model. And this question has been asked in recent years. So try to memorize these expressions as these can come in handy in the GATE examination. Next is something called as switching transient. As we study in network theory also, whenever we change the position of the switch, the transient behavior is observed. Transient is nothing but it is the behavior or the response of the system which lasts only for a short duration. It does not last for a long time. That is why it is called as transient, which means temporary. It is the temporary behavior. So same is the case with transformer. Whenever we will switch on the transformer, there will be some transient behavior observed which will last for a short duration and it will go away after the steady state is reached. Okay, that is called as switching transient. Usually this is studied when transformer is switched on. Now we consider that the switching transients are very severe when the switch is closed at the instant voltage is 0. Okay, switching transient is severe when on at instant when V is 0. If at the instant when voltage crosses 0, if you switch on the transformer, switching transient will be very severe, and it is least severe if you switch on at voltage is equal to maximum value. That I will show you why it is so, but you have to remember then switching transient are most severe if the transformer is switched on when the voltage is 0 crossing, and it is least severe when the voltage is maximum. Now there is something called as magnetic inertia. Inertia in a mechanical system is defined as property of a body by virtue of which it opposes the change in state of motion. Like if we consider the mass is also called as inertia. Why? Because higher the mass of the body, the more opposition it takes to move the body. That is, it is more difficult to move the body if it has a higher mass. It provides more opposition to any force. Similarly, in terms of magnetism, we will say that the flux cannot change instantaneously. Any inductor or any coil will provide opposition to the change in flux. That will be called as magnetic inertia. It means flux cannot change instantly. Okay, flux takes some time to change because any system or any inductor opposes the change of flux. Okay, so let us see how I was telling you this when the voltage has 0 crossing and voltage has maximum value. So for that, first let us draw the waveforms of the flux and voltage. So as I told you, the flux, if it is given by this, okay, then the EMF will be 90° lagging. 90° lagging means it will be starting from here, something like this, and the applied voltage will be opposite to the induced EMF, something like this. This is my applied voltage and this is my flux. So first instant that we were talking about when the applied voltage has 0 crossing. So let us consider this point when the applied voltage is 0. Let us consider this point as A. Here the flux is minus phi m. Okay, this is the flux required actually. The flux required in the core or induction of voltage or according to the applied voltage. Now if you switch on the transformer at A, the transformer requires a flux of minus phi m. But when the transformer was switched off, there may be no flux inside the transformer. Because the transformer is off, there is no current in the transformer, hence no MMF and no flux. Okay. During the switch off state, I can assume that the flux inside the transformer was 0. Though there may be some residual flux because we are talking about ferromagnetic materials. But still I am making an assumption that the flux was 0. Now if you switch on the transformer at A, instantly it requires a flux of minus phi m. But as per magnetic inertia, we cannot provide this much flux instantly. So transformer will not be able to generate this much flux. So what it will do is, how will my flux vary? The flux will only start from 0. Flux cannot start from minus phi m because initially the flux is 0. But then the flux goes from minus phi m to plus phi m. Here the flux will go from 0 to 2 phi m. Okay. The change in flux from this point to this point is 2 phi m. It goes from minus phi m to phi m. So the change in actual flux will also be 2 phi m. It will go from 0 to 2 phi m. Why does it start from 0? Because initially the flux was 0 and flux cannot change instantly. So it has to start from 0 only. But then it will follow the path of the required flux. That is, the change in actual flux will also be 2 phi m. But now if you see, the flux is twice the maximum value. And we know induced EMF is directly proportional to flux. So if flux is doubled, the induced EMF will also double. This is called as doubling effect. Okay. So induced EMF is also doubled in a short period of time. This is called as impulse EMF because high voltage is being generated in a short duration of time. Impulse is a signal which has almost zero duration. So short duration signals can be called as impulses. Similarly here the EMF induced is very high and it has a very short duration. So it can be called as impulse EMF. And such high EMF being induced in a short duration cannot spread through the entire winding. The thing is, there is some spreading time also associated with the winding. Whenever then EMF is induced, it takes some time to spread equally through the all turns. Okay. Otherwise, if we take a winding, the EMF is first concentrated around the edges like this. Suppose across these two turns on the top and on the bottom. But as time progresses, it advances from the edges to the center. Then it gets uniformly distributed across all the turns. But now we are applying a very high EMF in a very short duration of time. So it may not be able to spread through the entire number of turns, due to which it may be concentrated around the edges. What will be the effect? Since very high EMF is induced across the edges turn, it may damage the insulation. Okay. So what we have to do is, we have to provide extra insulation across the edges as compared to center of the winding. More insulation should be present at the end turns. The turns that are present across the ends of the winding, more insulation should be there. The next effect due to this doubling of the flux is, see, if we draw the flux versus I mu curve, it will have some saturation like this. So if this was my flux initially, the flux goes like this, 2 phi m, due to which magnetizing current also increases. And here the magnetizing current I mu 2 is much greater than 2 times I mu 1. Okay, due to saturation. If it were linear, the change in flux will be proportional to the change in current. But the curve is not linear due to saturation. The flux will require a high amount of current, due to which a very high current will flow into the transformer primary winding. Such a current is called as magnetic inrush current. Okay. So inrush current is nothing but It is the high current demanded by the core of the transformer due to the doubling effect. What is doubling effect? The flux generated in the core is double the maximum value because the transformer is being switched on when the voltage passes through the zero value, due to which the transformer requires a flux of minus phi m instantly, which cannot be generated. Hence, it covers the twice the maximum value of flux that we studied in the previous slide. Okay, flux get doubled, EMF also gets doubled. That is called as impulse EMF, and high flux requires a high current from the primary, which is called as magnetic inrush current. Okay, so inrush current is nothing but it is the transient current of a very high value that flows in the primary winding that can also damage the winding. It is almost 10 to 20 times the full load current. Okay, 10 to 20 times the full load current. Now, there is one other effect. As I told you when I was telling you about the interleaving of the windings, how the windings were being interleaved. Internally there was insulation, then there was low voltage winding, then there was insulation, then high voltage winding. I told you the current carried by these windings will be in opposite direction since they are wound on the same limb. And the forces that we studied were the repulsive forces. Between these two windings, the forces that are existing are the repulsive forces. But now, due to this transient behavior or due to switching transient, a very high current is flowing in the primary winding. That means this repulsive force also increases by a large amount. Since current is 10 to 20 times, this force will also become 10 to 20 times. Okay, and this current is restricted to the primary winding. It is not induced on the secondary. If it were being induced on the secondary, the forces would get balanced. The attractive and the repulsive forces would balance each other and there would be no danger. But now, these currents are restricted to only one side of the transformer, that is the primary winding. So, the forces will not be able to balance and this can lead to disintegration of the winding. So, windings should be provided good support, otherwise they will be dislocated. So, it can lead to dislocation of winding. Why windings will be dislocated? Because a high amount of force is being generated on the winding due to magnetic inrush current. Why it is being generated? Because forces are not being balanced, since this current is restricted to only one side of the transformer and not both the sides. Okay. Now, if you see, if we switch on the transformer when the voltage is maximum, where the voltage is maximum, this blue one is the voltage. So, voltage is maximum here. Here the flux demanded by the core is 0. And as I told you, flux cannot change instantly. Initial flux was also 0 and now the requirement is also 0. So, it will easily be able to follow the waveform of the flux and the maximum value will again be phi m. Okay, that means there will be no doubling effect observed. Doubling effect was only being observed because we were going from minus phi m to phi m, but actual flux will go from 0 to 2 phi m. Now here, if we switch on at B, we are going from 0 to phi m, so actual flux will also go from 0 to phi m. It will not get doubled. So there will be no magnetic inrush current present. But the actual switching would lie between A and B. So inrush current would lie between the maximum value and the 0 value. It will neither be actual twice the maximum flux and it will not be maximum flux. What I am saying is, if you switch on at A, the maximum flux is 2 phi m. If we switch on at B, the maximum flux is phi m. But if we switch on between A and B, the maximum flux would be lying between phi m and 2 phi m. Okay. That means we need to provide insulation across the end turns because the flux would be higher, though it may not be double, but it would be certainly higher than the maximum value. That cannot be avoided because we cannot make sure that we precisely switch on the transformer when the voltage goes through a maximum value. that is not precisely possible. The operating point may shift it may deviate from B to the left or the right. And if it deviates, the switching transient would be severe, though it may not be most severe, that is the flux may not be doubled, but it will certainly be higher than the actual value. Okay. And if we consider residual flux, the maximum flux can be 2 phi m plus phi r if residual flux is in the same direction, or it can be 2 phi m minus phi r if residual flux is in opposite direction to the induced flux. So it will reduce the severity of switching transient, it will increase the severity of switching transient. So in case the residual flux also supports the maximum flux, then the severity of switching transient will be increased more and more, because the flux will be increased, which will increase the magnetizing current required from the core, and it will increase the magnetic inrush current. Okay. So let us summarize what we have learnt in this lecture. We first saw the ratings of transformer. In that, voltage was proportional to area, current was proportional to area, KVA rating was proportional to area square, core loss was proportional to volume, no load current was proportional to length or the dimension. Then we saw switching transient. In switching transient we saw if you switch on when voltage is 0, maximum flux becomes 2 phi m, which is doubling effect. So induced EMF also becomes 2 times EMF, which is called as impulse EMF, due to which high magnetizing current, which is called as inrush current. This can damage the winding, so we need to provide more insulation, and this can also dislocate the windings due to large amount of force existing between the low voltage and the high voltage winding. So we need to properly brass the coils so as to avoid the dislocation. So we have to do proper brassing of the coils. So this is one non-ideality with the transformers, that whenever we switch on the transformer, a high amount of current is drawn. This we will see in the protection also. This inrush current can be treated as a fault by the relay. Why? Because the relay will sense a high amount of current is being flowing, so it may be falsified into thinking that there is a fault in the transformer. Always the inrush current will be high, so it must not treat it as a fault. Otherwise what will happen, the relay will open circuit the circuit and the transformer will be switched off. So that way we will never be able to switch on the transformer, because whenever it will switch on, it will demand a high amount of current, and the relay will sense there is a fault and it will switch off the transformer. So that is why relays must be able to differentiate between the inrush current and the fault current. Fault currents are also high, inrush current is also high, but it must be able to differentiate between the two. Okay. In the next lecture we will see about the harmonics in the operation of transformer. What kind of harmonics are there and how do they affect the performance of transformer.